welcome everybody to the Mayor's Megawatt Challenge from Plan to Action, measures to start your net zero journey. And the Mayor's Megawatt Challenge is sponsored by Enbridge. So just before I get started with a little bit about mayors and introduce our speaker, just some housekeeping notes. Please use the question and answer option for questions related to the content. That's down at the bottom of your screen in the black, in the sort of the black lined area down there. We will answer questions during a Q&A at the end of the webinar. Certain questions, if it's really relevant, will be answered during the webinar. Any questions we can't get to will be circulated in a Q&A document after the event. And if you have a technology question or you just want to introduce yourself or say hi, the chat is for all of that kind of conversation. So again, questions in the Q&A and we will answer them there. So a little bit about Mayor's Megawatt Challenge. Mayor's Megawatt Challenge is a program that's been around for over 20 years. There's a network of municipalities that's really focused on accelerating energy efficiency and greenhouse gas emission reduction and making buildings more comfortable for occupants. In the Mayor's program, we work on strategies to save energy and reduce utility costs, use the data to establish realistic targets and estimated cost savings potential, allow members to network and give an opportunity to share ideas so we're not starting from scratch, and be recognized for significant achievements through awards. And there's much, much more. Please do visit us at Mayor's Megawatt Challenge to learn more about the program, and feel free to reach out if you have any questions. The program itself is based on 4 pillars: energy management, based in the data; peer networking, which is working together on current concerns and issues around energy efficiency and greenhouse gas emission reduction; knowledge around case studies, best practices, new tools, etc., and recognition. We have an annual awards process to recognize top performers and others who are doing exceptional work. Next slide, please. I'm delighted to introduce today's speaker, Amandeep Diol, who's the Director of Engineering at Climate Challenge Network and has significant experience in a wide range of buildings, to talk about practical opportunities for saving in your buildings that you can implement right away. So without too much ado, I'll hand it over to Amandeep to take it away.
Thank you, Jillian. Welcome again, everyone. So let's get started. So we're going to cover, this is sort of today's agenda. So we'll cover sort of the first steps in getting to net zero, around where sort of operational improvements come in handy. What sort of a data-driven recommissioning process looks like, and how is that different from a typical recommissioning process that you might have seen in the past? How is the system sort of testing and metrics ties into data-driven recommissioning and producing results? We'll sort of look into some of the recommissioning measures that would give you immediate savings and sort of help build the confidence among your teams and the facility owners, managers, so you can sort of do more of that work and get some early wins. And we'll sort of, lastly but not least, we'll look at the building automation systems. We sort of touching on, if you have an existing building automation systems, what you could do to sort of reap those benefits now before you move on to other sort of ventures around FDD, fault detection diagnostics, or AI managed tools and other opportunities. But so the key is maximizing the benefits of the building automation systems and sort of leveraging the existing systems to deliver those. So those are sort of the key things we're going to talk about today's discussion. So let's get into it. So first step in getting to net zero. I mean, you guys probably have seen the slides a few other times if you've been to any of the Climate Challenge Network events or Mayor's Megawatt sort of webinars in the past. So why sort of this is important as a first step towards net zero, steps towards net zero, as few being municipalities or even in sort of other facilities, you've probably seen that there is a continuous sort of now urgency or demands around getting these buildings to net zero. Everybody is sort of trying to take that initiative, but there's certain paths you can follow. One of the sort of the first steps in that is your operational excellence, which is basically ensuring that what you have in the building, you're operating it as to its maximum potential, and then sort of moving on to the other pieces around heat recovery, solar or green energy or solar PV, geothermals, all of that, and finally the carbon credit. So it's kind of a, you start with the base energy emissions, you reduce that emissions by optimizing your systems, and then you do the heat recovery on those in your building, whether that's exhaust heat recovery or whether that's heat recovery from 24/7 load within the buildings. As an example, for ice rinks or pools, you can recover all that heat that is generated in the building and reuse in the building. And then finally, once you've done those two steps, that brings your EOI of the building to a point that you can look into solar PV and other areas for further reducing your emissions and also energy consumption in the building. And then whatever the remaining last piece is around renewable or sort of a carbon offset that you can purchase to offset that emission. So it kind of starts with developing sort of a low carbon sort of design briefs or low carbon study analysis, looking at your capital plans over the years and ensuring that you tie those together to kind of deliver you a net zero sort of a building that's going to run through all of these steps over the next 5, 10, 15 years, depending upon what you're trying to accomplish within your individual buildings. Today's topic, we're going to touch base. So we're going to have sort of series of these discussions, but today we're going to focus on the first step, which is around operational excellence. So what are some of the things that you can do right away? And what are some of the things that need least resources, least capital? And what are the things that's going to build confidence with your operational teams that when they see the immediate results, that will help them sort of push towards the next step in sort of further decarbonizing these buildings. So today's discussions and sort of the topics going to include the operational excellency, that is through data-driven recommissioning and air system testing and building automation systems. So how does that sort of process start? Like if you have a portfolio building and you want to understand which ones to focus, where to focus, everybody has their own sort of ways to look at their portfolio, but the simplest way to look at it is high potential buildings. So you kind of look at out of, if let's just say as an example, if you have 20 buildings, generally there's 80-20 rule. So if you look at from a emission perspective, if you have 20 buildings, 20% of those buildings would equate to generally 80% of the emissions coming out of those. So there's some high savings potential building in your portfolio that will deliver 70 to 80% emission reduction within your portfolio. And then you can focus, once you've sort of dealt with those high savings potential, then you can focus on the rest of the buildings. And this is coming from knowing that there's limited resources out there with your facility teams, even whether that's financial or human resources to sort of do this work. So having a means to focus on where you're going to make the biggest impact in the shortest period of time, the general approach is to make sure that you understand the high savings potential building and then start using the data, which includes utility data, intermediate data, building automation data, to achieve the sort of the early wins within your facilities. And that's what we're going to focus on today. Operational improvements. So the starting point to that is sort of making the connections with the target, savings potential, and the goals. So you may have, if you've done sort of any or reviewed any of the past webinars, we for the Mears Megawatt Challenge, we talked about setting up the targets for your facilities. If you haven't looked at it, if you go to the Mears Megawatt Challenge website, there's a white paper you can find on targets and target settings and benchmarking. So you can use that information to target your own or set the targets for your own facility, which will help you identify where the savings potential are. When you look at it, in certain buildings, you will find there's a high electric savings. There's certain buildings you will find there's a high gas savings potential. And what happens with that is that now you can sort of focus on, rather than sort of looking at the building as sort of a one collective means, you have the data now to support where to look for. As an example, if you see high heating thermal load, so heating thermal load is a load that the amount of gas you consumes to heat the building or to condition the outside air in the winter. So when you do the target sort of a comparison analysis or set the targets for your building and you see that heating thermal load being high, that kind of points you towards two things. One is if you have, let's say, enthalpy wheels in your building, so most likely the enthalpy wheels are not optimized. And secondly, it is basically driving that you're probably bringing too much outside air than what's required in the building. So having that sort of initial connections of target savings to your goals will help you focus on which are some of the measures you want to take on and where to find those using the power of the data. And that's what we're focusing on, is use the data that you currently have available through utility bills, through internal meter data analysis, through building automation systems. That is more than enough as a starting point to give you 80 to 90 to even 100% of the building's profile or the issues that can be highlighted through analysis of that data. And we'll focus on some of these analysis in today's discussion. Again, the main suspects, like when you look at it from, if you were to put a sort of a buckets around your electricity consumption, and then you see a high electricity savings potential, these are some of the main culprits in your sort of in your building that is driving that high energy consumption. So it's fan power, and fan power could be because of your systems are running 24/7, or they are consuming more watts per CFM than a typical fan should be consuming. So which means you have a high static pressure losses in your system. So you could have an inefficient lighting in your system. So having a sort of a lighting audit will help you sort of determine what are some of the sort of the savings potential on the lightings are, whether you have LEDs. If you do have LEDs, are they optimized for your building? Do you have the right lighting levels in your building? If you do lighting levels, are the lighting scheduled? Is there a protocol if you don't have a lighting control systems? Can you put a protocol with the securities? Do you turn off the lights when nobody's there? Have you done an assessment of your emergency lighting circuits to make sure there's not many emergency lightings in the building? Because sometimes what happens when you do get a lighting control system in place, you can actually easily move those lighting fixtures to a normal power fixtures, so that will help reduce emergency lighting if it's not required in your facility. So sometimes we see there's a lot of emergency lighting in the building. So similarly in the pumps, you might see there's throttling valve on those pumps, an easy measure. We'll talk about that in detail as well. Ensuring the right sizes pumps. Sometimes the pumps are oversized in your facility, so there's inefficiency that comes in the pumps, and they're not able to reduce the speed on those pumps because then they're limited by the motors, what they could do. Differential pressure control, again, a simple measure where you're doing a field investigation of those and making sure that the field set points are actually calibrated back into the systems. And we'll talk more about that in a second. Again, with air conditioning equipment, you have the right sequence of operations. These are some of the sort of high ticket items. We'll talk about how they fit into your recommissioning, retrocommissioning process, and how you can leverage the power of the data to achieve savings or do initial sort of operational measure improvements in your facility. Similarly, if you see a high thermal savings potential when you set your targets for your building, you will see some of these male culprits. Like you will see if you're outside quantities, like how much outside are you bringing? Do you actually know? This is pretty good measure that recently came into a lot of highlights, because what's happening with the fires and the smoke, the ventilation systems are being sort of becoming more prominent, and everybody started talking about it. So understanding for your facility, if in an event that your facility has to operate for certain reasons during those kind of catastrophic events, do you actually have tested your systems to understand whether you can actually run your systems during the time if it's needed? If it's not needed, yes, there's no point sort of that additional controls logics to be put in. But for some reasons, if your facility is being sort of considered as some of the shelters or anything for the community, could you run your facility without in those catastrophic events? So building the resiliency for your facility does come through these operational measures as well. So perimeter heating systems, looking at whether they're not making sure they're not running in the summertime, ensuring that they have a separate loop so you can turn them off in the summertime, having an outside air control based on the supply water temperature, so you can reset the water temperature as outside air temperature changes in the bill or changes outside, ensuring that your boilers are delivering the right efficiency, they're not cycling. We'll see a couple of examples on that. And then space temperature resets, like you have those night setbacks in your facilities, so when nobody's there, you're not conditioning that space to the same temperatures as you would condition when somebody is there in that facility. Again, this is all coming from, so if you haven't been to the Mayor's Megawatt Challenge, I would highly recommend you looking at the website again. There's a lot of collateral, there's a lot of publications that will help you sort of optimize those buildings, and there's a lot of content that we wouldn't be able to talk it through today, but you can actually read on your own time about these systems. So our pool cohort project, sort of a research project which was recently completed, kind of list all these measures, and these operational measures that are low cost are listed here, which again are more focused on how do you operate your pool, whether that's the water temperature or the pool equipment itself during the unoccupied periods, because that's where you're going to get majority of the savings, is to ensure that you get the right unoccupied set points, both on your pool's water temperatures and also on the relative humidity and the temperature in that space as well. So ensuring that you're not over ventilating that space. There's schedules of sort of put on those systems. Again, low key, very easy to implement these measures through your building control automation systems. Similarly, again, on ice rinks, you will find a lot of content available through an cohort projects that was recently completed as well. Again, some of the very sort of operational measures that could be implemented within a day, doesn't need a lot of sort of a capital, just programming changes. So you work with your facility folks, try these out and see how things settle. What are some of the temperatures that's something that operations teams are comfortable doing that, and that will sort of deliver those early wins for in these kind of facilities. Operator training, again, this all sort of goes back to how do you involve your building operations teams in all of these projects, and we'll talk more about that in when we talk about data-driven recommissioning. One of the key aspects is to have organizational alignment. So generally, when we see is that even if you bring a third-party consultant to help you optimize your buildings or do operational improvements, the key is to make sure that your facilities operation teams is heavily involved in that whole process from start to end. So the thing is, facility operators actually know the building best than anybody else out there. They operate those buildings 24/7, so they know what are some of the limitations of those buildings and how they're trying to manage those their topmost priority of occupant comfort. And they're the one that will sort of help you guide with the help of the data to help you understand the building performance and find you anomalies that a third-party consultant may or may not find, whereas the building operations teams will help with the guidance of the data-driven approach. They can actually pinpoint those issues and help them sort of identify those issues and then help them fix them. And once they have this sort of a opportunity to work while they're on the job, it helps them sort of build that confidence and then help them create some sense of accountability that they love to participate in that, and that accomplishment they get through this whole process is generally we see a lot of people sort of talk about it even after the process has ended, and they tend to deliver or sustain those savings over the years after that. Let's quickly talk about the data-driven approach of recommissioning. How's that sort of different? And how's that fits into the operational improvement or operational excellence we talk about here? So let me just go to the next one. Okay. Sorry. You have heard these terms: recommissioning, functional commissioning, operational commissioning, retro commissioning. they're sort of similar terms, but sort of have slightly different meaning to them. So a typical recommissioning process, or you can call it a retrocommissioning process. A recommissioning process you associated with basically a new construction building where you're completing construction, your recommissioning agent who verifies the functional aspect of the building. 99% of time, that's what they're hired to do, is a functional aspect, which most of the times looks at whether a handling unit turns on and off, whether fans has a VFD, whether sequences have been implemented. But what they don't look at it is the performance aspect of that equipment. So what I mean by that is whether that equipment is actually running as it's supposed to run. For example, whether the fan, what is an expected profile of that fan? Is the fan actually scheduling? Is the fan VFD actually at 90% or during the day? Is it supposed to be at 90% or is it supposed to be at 80%? What is the consultant was expecting that VFD to operate at? And what was the owner expecting that VFD to operate at? So that is sort of an operational excellence where it comes in to ensure that not only their equipment is sort of operating as on off or sort of as in operationally it's working, but it's also optimized to achieve the lowest energy consumption in your building. So a recommissioning process sort of a retro recommissioning process looks at working through the existing buildings, where recommissioning process looks at existing buildings. Again, these are terms that are interchangeably used in sort of the industry, but the idea is to ensure that you're sort of doing that exercise on a regular basis to make sure that your facility is operationally as good as it could be. And it all goes back to the targets. Like when you compare your facility against a top performing facility and you have high savings potential, that means the initial thing to do is looking at the recommissioning or recommissioning aspects of that. Now, a typical recommissioning process uses some amount of data. It's more of an observational views of how the equipment is performing. But a data-driven approach sort of has sort of these three pillars. It looks at the technical aspects of that sort of operations of the equipment. It looks at the building automation system. It also looks at organizational aspect as well. But all of this is done through a data-driven approach where you initially set your target for your facility. You look at the targets, you do a component analysis of your utility data. Then you sort of look at which of the components are sort of a high savings potential. Then you further sort of look at that savings potential or sort of a component through the intermeter data analysis, whether that's your electrical intermeter data analysis or your gas intermeter data analysis. If you have further sub-meters, you can use that for certain component analysis of those subsystems. But then it goes back to your building automation systems. How are your sort of, what are your systems supposed to do for a high performance building? What is it exactly doing right now? And that's all driven through a trend log analysis. One of the other sort of, traditionally what I've seen on the recommissioning projects is whenever a consultant is engaged by a building owners, they've been tasked to recommission a building and bring it back to the design. Where I see that challenge with that is that we don't know if the design is actually the most optimized operation of that building. So what this data-driven approach does is it lets you know when you compare your building against a high-performance building, it sort of gives you an opportunity to see whether your design is the best sort of optimized operating sort of solution, or you have another solution that you need to implement as a part of this decommissioning process. So the idea is to sort of keep that sort of horizon open to make sure that you not only looking at your sort of design as at the time of the recommissioning process, but also looking at what are some of the best practices out there to operate this facility or operate this building. So as an example of air handling units, if the design is calling for, let's say, a sequence that doesn't enable your fan to be optimized, then design is probably not the right solution to look for. Then you have to look at it, what is my right optimized sequence of operation for that equipment? And that's where the data comes in. So again, the idea around data-driven commissioning is to find out what are some of your high performance metrics. So when you do that data logging of your lighting systems, an easy metrics to look at that is what is your watts per square foot for lighting, and if that, so let's say if you have an LED lighting, and if that watts per square foot is a 0.84 watt per square foot for your facility, definitely there's overlighting in your building, because generally those lighting numbers should be anywhere from 0.25 to 0.5, 0.6 watts per square foot for your facility. Typically, it's in that range when you implement a LED lighting project in your facility. Similarly, on the fan power density, like what's your watts per CFM? When you have a tap contractor engaged for your facility, and then when they're measuring your CFM and measuring the sort of the motor horsepower and brake horsepower, you could have them calculate the watts per CFM and have that compared against your design values. And if you see there's a discrepancy there, that points to there's probably more pressure that system is trying to overcome than what your system is designed for. That gives you an opportunity to sort of optimize that system. Similarly, on the boilers, we talk about that, how the boiler efficiency and the boiler testing helps you sort of drive this process, and intermeter data analysis. So looking at your peak unoccupied and occupied power densities and gas profiles helps you determine how much scheduling is happening in your building, and comparing that against other facilities. When you see your daytime consumption of your electricity as a peak, as your system comes on, you use the highest amount of electricity during the day, and as the systems drop during the nighttime, which is ventilation, cooling, and heating or pumps, you will see that the consumption start to drop. But if you see a flat profile and an interval meter, that tells you your equipment is running 24/7, and then you have an opportunity to schedule those systems. Using the building automation system, we've heard a lot of talk about fault detection diagnostics tools, and recently we did a webinar on that as well. There's talk about AI being used in the facilities. There's talk about other sort of automated fault detection diagnostics that could help sort of use this building. But I think what we were saying is the starting point is use your building automation systems first, because you already have a tool that hasn't been optimized yet. So using that tool to optimize your building, and then you can leverage the power of the other tools as you've done the optimization on the building automation system. But the starting point is, if we haven't fully used the potential for the building automation system, adding another layer of controls on top of that, it's going to complicate more things for building operations teams. And then there's fatigue that generally comes in with a lot of that data, and then they will tend to sort of feel burdened by a lot of these data sources that are coming in without any sort of key actionable items. So we would suggest is to using the building automation system in a data-driven commissioning to optimize your system. And starting point is looking at your scheduling, looking at your set points, demand-based controls, and then ensuring that you have a trend log set up on your systems. So anybody who is looking at that systems, they could do historical analysis on that, and the trend logs are available to do that analysis based on the operations. Because for any facility, you need to review that historical data for a full set of years, so you can look at different seasons, how the building is operating in your shoulder season, how the building is operating in your colder weather, and how the building is operating in the summer weather. So you can optimize all those 3 seasons for the peak efficiency of the building. Another thing is, like, we sometimes look at these things in a silos. You will see a capitals being done in silos where capital teams are developing their projects and operational teams have a less feedback on that. Eventually, there's a capital project that get delivered to an operational team. Operational team didn't have any feedback, and now they're kind of stuck with a project where they have to sort of reinvent the wheel and learn all of that through actually operating that facility. So having that organizational alignment around capital planning and asset management is a key for any facility to achieve net zero. Without it, it's really going to be hard because organizational alignment makes sure that your resources are committed and make sure that you have clear direction from your organization to achieve these. And it all starts with different projects. Even if you're doing a simple projects that are recommissioning in your facility, ensuring that this is driven by an organization is not a solo project, because the commitment that you need through that process is going to involve a lot of changes that has to come from an upper and senior management level. So making sure that you have a commitment from the occupants, you have a commitment from your corporate team. Then the path is easy. You get a savings that are delivered. But the key thing is the savings are sustained once our organizations are aligned. What we see in 90% of the time, where you bring a third-party consultant, they make the changes, operations teams or organization is not involved. You see some savings for 6 months or a year, and suddenly the savings start to disappear as the effect of that process sort of diminishes, because then the initial engagement between the operations team, that organization wasn't in line, and everything sort of falls back to that square one, and then you end up being in the same place after done that whole project. So the key is to make sure your organization is aligned to deliver these kind of big projects, and also ensuring that your capital and asset planning is aligned with your low carbon solutions. And one of the key things that we noticed in that whole process is that a lot of the times there's not enough lead time for the projects to get designed. So what happens with that is low carbon alternatives are not considered for those, and it's more like a like for like replacement were to happen, because your rooftop unit is about to break, or it's actually broken, and you need that equipment running in the next month or so. You don't have enough lead time to do all the low carbon alternatives. So what ended up happening with that kind of approach is that you always tend to get a like for like replacement. In this case is you'll probably get another gas fired unit, which may not be an ideal for your net zero goals, because it's really going to be hard for any equipment that is put in now. Has an asset life more than a 2050 target of net zero, and some of the municipalities have a lower targets of net zero as well. So think of from that perspective that any equipment that you put has a sort of a carbon associated with it, whether they're burning fossil fuels, they would have to be either gutted out or removed from the facility to reduce that emission in that facility by the set targets, whether it's 2040 or 2050 for your municipality. So ensuring that your capital planning is aligned with your long-term vision of net zero is a key, and you have a lead time for all of these big capital projects, and they're aligned with your energy efficiency goals as well. Now, this kind of brings us to, we talked about data-driven sort of commissioning. We talked about using system metrics as a keys to sort of drive those operational improvements. So we're going to look at some of the key system metrics and how you can sort of use that information, or sort of how you can engage your contractors to do the testing in a way that helps you understand the sort of performance of the systems, and you can implement more of those measures with a data-driven approach. So the system testing and metrics applies to all the system, whether that's air handling systems, boilers, hydronic systems, or even sort of electrically circuit, like your data loggers could be used for your lighting, for your plug load, or any process load in the facility. So the idea is to engage the contractor to do the testing, but has a means to the testing. The testing is there to help you understand the performance of the equipment. And there's some certain metrics that you want to use to understand the performance of that equipment. And that sort of is driven. So let's take an example of air testing and balancing. So when you engage your consultant or sort of a contractor, you would ask them to test these systems. So they would measure the airflow. They should measure the airflow. They should measure the pressure drop across each component of the handling units. That's your outside air damper, your heating coil, cooling coil, your fan. And then you will see that when they report that information back to you, you will see that some of the components have a higher pressure drop than what your design originally called for. And that is an indicator that it either tells you, in some cases, for example, your heating coil or cooling coil is clogged, or your outside air damper, there's probably a mesh there in front of it, it's clogged, or your outside air damper, it has a too much pressure drop, which means that your unit is starving for air, which means that your turn fan is probably underperforming. So here's one example here. So the original design for this HU1 calls for 42,000 CFM at 100% VFD speed. When the system was tested at actual operating condition, the VFD was around 68%. So the expected airflow for that system was around 29,000 CFM. But the system was running at around 19,000 CFM. So it was under sort of performing for the expected airflow, which means that there's probably system is spending more energy on overcoming the static pressure than delivering the airflow. So that underperformance is sort of gives you an opportunity to optimize the system. And when it's optimized, it should deliver more airflow, which means that it could even further slow down and hence save energy on motor consumption for this particular fan. So another key thing is, as you look through these systems, you drive these systems through or sort of analysis through watts per CFM. So if you're not sort of currently engaging the contract, again, this is not a additional work. This is basically, they have all this information. So they'll measure the watts for that or kilowatts for the particular fan. They measure the CFM. So you divide this two, gives you watts per CFM. And if you see that, and you look at that watts per CFM, and you compare that against two metrics, one is your design, and the second is your high performance systems. If you see that high performance system, watts per CFM, let's say is 0.6, and your actual testing is, let's say, is 1, and your design was calling for 0.7, you know that your system is underperforming, and that's where you start to investigate on this particular systems, why the subsystem. And some systems you will see that after you do that sort of a metric analysis, that the subsystems are performing as they were supposed to, then you can sort of eliminate those from your analysis, but leave the rest one, and that will help you pinpoint where the issues are in your system. Here's just another example that, and sort of an observation you wouldn't notice without the air testing of the systems if this was not done. So in this case, what you see is you have a supply fan here, which was trying to pull the air through the outside air lure. You have a return fan and a mixed air system. So what's happening is that the return fan was designed for 41,000 CFM and is actually delivering only 27,000 CFM. But the supply fan is running at actual condition of 53,000 CFM. So which means that the supply fan still needs to make up that 53,000 CFM. So it only is getting half of that 27,000 approximately from the return fan. The rest of that it has to bring from the outside air. So even the outside air, it's trying to bring it through the outside air lure is not enough. So the air found the least resistant path, which is through the exhaust air duct and back through the exhaust relief duct. So when the system was tested, they noticed that the exhaust relief duct was actually became an outside air intake for the system because the return fan was underperforming. So in a normal observation, you wouldn't notice that issue. You will see that return fan running at 81%, that's fine. The supply fan is 81%, so the system should be working fine. But that's not the case here. Like that system wasn't working fine. And the only way was to find through the air testing system, or testing these systems. So what happened was that when the fact, well, two things happened here. One is it was bringing outside air through the exhaust sort of relief duct, and then it's bringing, as a result, because the return fan was underperforming, it was bringing more outside air, like 49% outside air when the system was only requiring, I think, 33% or lower outside air. So once the return fan was fixed, the CFM was corrected, the outside air sort of percentage also got corrected as well as a result of that. And sometimes we see that, well, actually, let me hold on to the thought. I'll explain that in the outside air section. But again, system air testing is important. If you haven't done an air system, that's the starting point to understand the performance of your system. Boiler efficiency testing. You have your boilers contractor coming in, doing a regular checkups and regular sort of thermal efficiency performance testing. So this is some of the things that you should request from your sort of your boiler testing contractors to give you the performance of each of the boilers. So now what you're seeing on this is on the right side is your total efficiency of the boiler at different stages of the boiler as they're operating. And then on the left-hand side is your flue temperature leaving the boiler. So as you could see, higher the flue temperature leaving the boiler, which is the gray, in this case, the lower the efficiency of that boiler, which is gray on the left-hand side of it. So, and then you could also see that the boiler efficiency starts to improve in this case as it's running in sort of a low operating condition. So again, your efficiency curve for your boiler will be unique, and it could be similar to that, it could be slightly different. But knowing which boilers performs better under which condition is a key, and then you can reprogram your building automation systems to use that boiler and ensure that you get the best benefit out of the existing boiler heating system and optimize those systems accordingly. We talked about sort of the procuring and testing is another key thing that comes in, like how do you know who do you contact and who are some of the players out there. There's a couple of associations. I mean, AABC is one of them. There's NECB, another one. As long as you have a certified tap contractors, that is a good start for you to sort of review your building system. But the key is to give them directions around what you need to get tested, because you need to understand it's basically if you want to use an analogy, the tap contractors are like your lab. If you go to a doctor, you need somebody to write specifications for that. And the tap contractor is basically in lab, in this case, they're going to perform that test for you. But you got to make sure that test you write to them is the right test that will help you understand the performance of your building, which is making sure that you get them to measure the right components, you get them to measure the right data, and then have them document data and give it to that in a way that you can understand that report and have sort of analysis come out of that will help you find those inefficiencies in your system and implement those. Again, that's all data-driven approach. That's where it's different from the observational reports or observational approach, where equipment observation is really hard to tell you or pinpoint where the operational issues are, whereas data-driven actually pinpoints where the issues are in your facility. Now, let's look at some of the typical recommissioning measures that you will see. Again, in your facilities, ensuring that your building systems are running as designed or as a high performance, again, what a high performance building should look like. Majority of the times we see the low key measures around scheduling. We'll talk about that. Temperatures, right amount of sort of right set points are used in your space for relative humidity and the temperatures. There is some night setbacks being placed in occupied modes, and then you're managing sort of using variable frequency drives to optimize the building in low load conditions when there is sort of opportunity to reduce the consumption of the building. Scheduling, again, very simple measure. A lot of people sometimes question, why are you still talking about scheduling? And then the feedback we get is there's still so many facilities out there where systems are not scheduled. And it's really easy to sort of talk about fancy stuff of decarbonization, like heat pump systems and electrification and everything else. But if we haven't done the fundamentals around scheduling these systems, we're not doing it justice to the building operations. So the key is, if you have a system that whether you can partially schedule it, whether you can completely schedule it, make sure those schedules are very sharp, in a sense that you're not sort of first point is to sort of start some sort of scheduling, then is to refine those schedules over the time. You might see that initially there might be some pushbacks from some of the areas around because they might not be used to the idea of systems being scheduled in the past, because the systems have been running 24/7. But there's a process that you can follow through and help them understand why you're doing these, and how is that important to the goals of the organizations and achieving those climate sort of initiatives and targets in your facilities as well. So the key is to find those opportunities. Most of the systems should be and will be scheduled in your facility, and find what is needed in those facilities to schedule. So, for example, if you have an area with a partial occupancy, you can install an occupancy sensor, have your unit control the ventilation systems to that air, or sort of ventilations to that space. You can still recirculate the air in that space, but only bring on sort of the ventilation air when it's needed as per the occupancy. There's many means to sort of further optimize those systems, but having an initial occupancy scheduling is a starting point for any operational excellence in a building. Again, with we talked about sort of using the ventilation systems and using the VFDs to optimize your systems. Most of the times we see that the VFDs are controlled by static pressure sensors. In this case, here's an example. So on the left-hand side, you see two units, blue and red, with the static pressure set points fluctuating from 300 psi to 350 psi different times of the day. And then as the unit shut down, the static pressure goes to zero at nighttime. These static pressure set points are, I would say 99% of the times, are arbitrarily set during the initial sort of programming of the systems, and generally set too high on the system. So what happens with that, if your systems tend to waste a lot of pressure trying to satisfy those high static pressure set points, and it wastes a lot of energy on those systems. So the measure in this case, what was done was those field investigations of these static pressure sensors result in resetting these static pressure set points to a lower value. So as you could see, the blue on the left-hand side and before it was around 300 psi, it was reduced to around 250 psi. And similarly, red, which was around 350 psi, was reduced to a 250 psi, or 250 Pascal once the field investigation was complete on the static pressure reset. So, and as a result, the VFD dropped down, and there were significant savings on the electricity side for this fan as well. So you will still get the same airflow, but what happens is that now the pressure you were wasting by setting that high static pressure in the system, that pressure is now reduced, and now their system's working less harder and hence delivering the same airflow, but with less energy being used to deliver that. So the key is to, again, do the field investigations to make sure, find what is the right set point so you can achieve the airflow at the sort of the most critical run of your HVAC system or sort of ductwork, and then use that as a means to reset these static pressures. Thermal wheels, again, 95% of the times we see these are underutilized. You would have a heat wheel that was originally supposed to recover the heat from the exhaust air and then put it back into the supply air. And most of the cases is an enthalpy wheel, which means it not only recovers the heat, but it also recovers the moisture as well. So which helps you with lowering your humidification load in the building, and as well as lowering the heating load in the building. But in most of the cases, what we see is that preheat coil, which is there to protect the wheels or sort of protect the wheel from frosting, its set point is set too high that what it does is it basically limits the operation of the wheel. So as an example, this unit was sized to bring in -15 as an entering air temperature, -15 degrees C as an entering air temperature to the wheel. The preheat set point was set at 5 degrees C. So what happens is that the incoming air, anything below 5 degrees C get heated up by this preheat coil, and then it gets delivered to the wheel at 5 degrees C. Now, wheel could only deliver an air with which is sort of able to recover. So 5 degrees C would only be able to get to 10 degrees C on this wheel because it is limited by the exhaust air temperature as well. Now, if this wheel was operated correctly, I'm just giving this as an example. If this wheel was operated correctly, the preheat set point would have been -15, which mean that any times the air is sort of between -15 and higher, there will be no preheat coil used in the wheel. So the -15 will come in, hit the wheel. It will have a 20 to 25 degree delta T, which will bring you to around 10 to 12 degrees C. And that's what you need probably in most cases, the supply temperature. So you probably would, with the wheel, if it's working appropriately, you would hardly see this heating coil coming on, which is the one after the wheel. And most of the times, your wheel should take care of all the heating load on this air handling unit. So If you have a thermal wheel, there's sometimes we see other challenges around shoulder seasons operating these wheels. You get a high fluctuation in the supply temperatures. All of those issues could be addressed easily through programming changes and optimization. So if you have a wheel, one takeaway if you want to take from this session is go ask your operators, what is the entering air temperature on the wheel during, if you want to take an example of this year. So if you look at the month of January, I think third week of January was the coldest month this year. So if you see your entering air trend point on the wheel, anything less than, let's say, -10, -15, and your wheels originally designed for that low intake air of -15, then your wheel is not optimized and you can use that opportunity to optimize the wheel. This is one of the measures where you will significantly drop the gas consumption in your building because the wheel is underperforming in this condition. Another one we touched on briefly in the previously was when you see a high heating thermal load in your building, most of the times it's pointing towards how high outside air in your building. So what's happening here is, as an example, your blue dots in this case, I'm not sure why the color changed, but the blue dots in this case is your outside air percentage. The orange dots in this case is the heating valve position. So as you could see, when the systems in this case was required to deliver 33% outside air. So in your case, it could be different. It could be 15% outside air. It could be 20% outside air. But you know your threshold. So if you look at this system and then what's happening here is if this is the red line, that is how much outside air that system needs. But the system is delivering more than that. So in case of when it's -30 outside, it was delivering 43%, and then it starts to increase the outside air percentage as it gets sort of a little bit warmer outside. And the another thing is the heating valve is running during all this time. So you're supposed to run 33% outside air, you're running at 44%. So that extra outside air you're bringing into the system is now needs to be heated, and that's where most of the heating thermal energy goes in your building. So ensuring that you're bringing the right amount of outside air when your heating valve is running is the key to make sure that your building is optimized. And the way to do that is you could set up an easy point on your building automation graphics that uses the temperatures to calculate the outside air percentage. And then that point is always there for building operations teams. And you can also put a set point underneath that. So you know that based on your outside air ASHRAE 62.1 calculations, your system is designed to bring in, let's say, 15% outside air. And then during the extreme cold conditions, when they see that the system is bringing 20, 30, 40% outside air, you will immediately know that your system is not performing as intended, and then you need to rectify that. And in most cases, it is a sort of a indicator to, if you're seeing too much outside air, most of the times it's the return fans and the supply fans are not balanced. Because if your return fan is not delivering what your supply fans needed, then the supply fan is going to draw the outside air regardless of whatever you do with the dampers, because dampers then becomes air sort of doesn't come into the equation because the system still needs that airflow. It's going to draw through the outside air lower regardless, because the return air is not there to sort of fill that gap. Boiler plant investigation optimization, again, another key measure. Some of the simple thing is looking at your boiler sort of graphics and seeing, do you actually have an outside air reset on your boilers? Is your boiler temperature resets? In some cases, you're limited because you're providing that hot water for your domestic hot water heating. But in other cases, if you have separate domestic hot water heating, then you could lower your supply water temperature for your boilers based on outside air reset. And again, in certain cases, you're also limited again on the return water temperature limitation of these boilers. If they're not condensing, you might have limitations on how much return water temperature or what temperature you can bring back to the boiler. So working with your boiler manufacturer, working with your controls contractor, ensuring that you have some sort of an outside reset being put on these boilers, so you can maximize the savings on the boiler plant. Few other things around boiler cycling. That's another one we see sometimes is you have few boilers in the building, they're not talking to each other, and each of them are controlling their supply water temperature at their own headers. So the water leaving, so the boiler is looking just at the water leaving the boiler, and it's not looking at the common header supply water temperature. So here, that was one of the sort of the issues that we found in this facility was in the left, you see that 3 boilers, even though there was a minimum load on these boilers, but all of them were coming on and they were cycling heavily. And the reason for that was they were not talking to each other. So each of the boilers were individually working. What it was doing, it was set at, let's say, 160 degree Fahrenheit. And then as the water was leaving the temperature, or as the water was leaving the boiler, the boiler is only looking at the leaving water temperature of its individual boilers, and then they were coming on and off, on and off, on and off. That was easily fixed through a sort of a controls upgrade. So where the boilers were started looking at a common header temperature. Hence, for the same time period, only one boiler was needed, and as a result, like you could see that at any given condition, only single boiler was running, whereas previously the 3 boilers were running because they were not talking to each other. And you can sort of run this trend analysis. This is status point for a boiler on your building automation system, and have a look at it, like how your boilers are doing in summer, how are they doing in shoulder season? Are there 2 boilers running, 3 boilers running? Is there supposed to run 1 boilers? And a lot of time your building operations teams would know that if you have a cycling issues, they could see that their 2 boilers are coming in when they're not supposed to come in. Again, with the chiller optimization, the starting point is look at your delta T in your system. And then you go back to your design, check what was your original design delta T for your system, look at the chiller manufacturer recommendations. If your system is not delivering the design delta T, that is your starting point to start to understand where the issues are coming from. Because a delta T, a low delta T syndrome in any facility is generally points to whether you have too much flow, which is you're pumping energy being wasted, and as a result, you're delivering sort of your system is underperforming. And what happens with a low delta T is that your chiller is not optimized. It runs at a low efficiency all the time. So making sure that you get the right delta T in your system is a starting point, and you have to look into why you have to overpump the system, and it could be that you're not able to achieve the water flow at the end of the line, and there's sort of a lack of cooling there. Maybe there's other issues that is causing that. Maybe the cooling coil is blocked, or maybe the cooling coil is not cleaned. And maybe there's originally the cooling coil was not sized for that sort of load. So, but what happens is that and as a result, you're sort of driving the chiller hotter, and then it results in inefficiency. So having a pulse at the data itself, and then some key observations from the graphics will have you start sort of down that path of looking at chiller optimization. Another simple measure like pump optimization and controls. In occasions we've seen that in a sort of related to glycol pumps, that they're generally labeled based on outside air temperature, which is fine, but I think once they're enabled, they're always running. You can use some smart sequence of operations, and especially if these pumps have VFDs, you can actually look at the heating valve positions on the handling units and optimize the glycol pump operation based on them, rather than having them run 24/7 based on the outside air enable point. Have them run when they're actually needed in the field, and you can always sort of slow them down and have them sort of a minimum speed run if you're concerned about providing an immediate sort of heating to the system during the extreme cold conditions. You can set up a sequence where it runs at a minimal operations and then speed up as your valve open and your differential pressure set point drops in the system. Triple duty valves. If you look on the left or right side of your screen, you'll see a typical configuration where you have a pump, you have a triple duty valve, and then and then you have a VFD in your system. So if you have this kind of configuration, I would highly recommend you to look at your triple duty valve position. These triple duty valves sort of in the past were used to balance the system and there was no VFDs. And then when the VFDs were put on these systems, the triple duty valves are generally left as it is. So, but the idea is to make sure that now you're using your VFD drive to balance the system, not the triple duty valve. So what you could do in those cases is you could sort of use a rent and ultrasonic flow meter and put that on a pipe and measure the before flow, open that triple duty valve fully, and then slow down your VFD to match with the before flow. So you're not optimizing the flow here, you're just keeping the same flow as it was before the triple duty valve was closed. All you're doing is removing that extra pressure from the system, and as a result, you're still able to achieve the same flow by running the VFD at a lower speed and hence saving energy. You would also see where you have a pumps in your system and you have a VFDs, you will see a differential pressure sensors in your buildings. That differential pressure sensor generally controls the VFD speed, and you will see a differential pressure set point on your system, and you see a differential pressure actual on your system. What your pump or VFD is doing is trying to match that differential pressure set point. Now, in most of the cases, this differential pressure set point is an arbitrary value that's set up in the field. But we highly recommend you to field test that differential pressure system to look at, first determine what is your longest or the critical run in your system. And then on that critical run, measure the pressure drop across the end of the loop and see how much pressure do you actually need in that system. And then rebalance the set point to a lower value to achieve that set point, and as a result, you would see that VFD speeds drop because now it is trying to achieve a set point which is lower than a previously arbitrarily set point. So if you haven't done a field investigation on the differential pressure set points, again, highly recommended for a pump optimization measure. So these are some of the sort of the high level measures that you can immediately apply in your building, needs least capital, needs get your operational teams highly involved, and sort of delivers you immediate savings. That's your first goal towards sort of resetting your buildings or sort of having that sort of first step met in optimizing your achieving operational excellence. Just a few more slides on the building automation systems, and then feel free to sort of throw in the questions as you sort of look at the slide decks, and as you have some other observations, please fill in your questions. Now is the time, and we can address those as it comes to the end of this. So building automation systems, again, a lot of information you can find on the building automation graphics with your operations team. So here's an example there for this particular building. These pumps were sized for duty standby, however, 2 of the pumps were running. And an observation that you can see from the graphics itself, but that will help you sort of, again, small, easy wins that you can do as a result of optimizing these systems. Economizer mode, this again, we see a lot of the times in the facilities is you would tend to assume sometimes that the building is commissioned, the systems or the controls should be running as optimized. The economizer should be running as intended. So the economizer, if you're not aware of what economizer is basically a sort of a combination of the dampers that is used in air handling units to reduce your cooling load in the facility. So in case when you have cold outside airs, rather than using the chilled water system in the building, you're utilizing the outside air to cool their building. So in this example, the system was running, was starting to produce a 58-degree supply water temperature or supply air temperature. Outside air was 62. So what was supposed to happen as a system in the economizer mode, the mixture damper was supposed to open more, which means that you could bring in more outside air and mix it with a little bit of return air to get you 58. You don't need any of the cooling because you have a cold outside air that you can utilize and don't have to use the return air. But in this case, the mixed air temperature was higher because there's too much mixture or too much return air being mixed with outside air. And as a result, the cooling has to be enabled, which means that your now chiller is working where the countermiser mode would have done the job and you wouldn't have used any of the cooling in the building. And again, simple observation that a building operations team could notice when they're looking at these graphics and sort of engage their controls contractors and consultant to help them optimize these systems. Similarly, again, in many of the facilities, you might see that the CO2 sensors are now being used to track the occupancy in the space, which is another proxy to control the amount of outside air that you bring into the building. And if you're seeing a high level of, you're seeing a low parts per million of CO2 in your facility. So generally, I think now, depending upon the area, you could see anywhere from 400 to 425 as your outside air parts per million of CO2. Whereas if your return air is seeing anything less than, or anything around 550, 600, that's a good indicator that you're bringing too much outside air into the system, because if there's people in there, you should expect to see a higher, like anywhere around 800 to 900 or even 1,000 parts per million of CO2 in that return air. So if you're seeing a less air, which tells you two things: either the occupancy is low, or secondly, you're bringing too much outside air into the system. So again, that's another way to look at the BAS graphics, as a simple way to understand where the issues are in the facility. That's kind of sums up like what we sort of try to cover this, and I know we have a little bit of time left, but I'm happy to sort of address those questions. But I want to sort of again highlight some of the key takeaways on today's discussion. One is recommissioning, data-driven recommissioning, right? So we'll highly recommend using the system level metrics to drive those measures. What it does is it sort of helps you use the data that it's already existing available within your facility, helps you pinpoint the issues, and helps you engage your building operations teams, which otherwise wouldn't be engaged in that whole process. Because when they're engaged with the understanding of the pumps, understanding of the measurement of the data, having those reports reviewed with them, they sort of tends to document that issue, they tends to connect with it, and then help to sustain those savings. Looking at sort of the recommissioning ask, so when you're going out there requesting the recommissioning work, try to sort of focus on, if you could, on the performance-based outcome, like what you could do with your commissioning consultant, or even on new performance or new construction buildings. And if you get your consultant to look at the performance of that sort of equipment, and in addition to the functional aspect of it, that will ensure that your buildings are delivering the right amount of savings from day one, and you don't have to spend another exercise optimizing those systems. Because what happens in that process is, if it's only functional commissioning and there's no performance sort of based outcome commissioning, you will not see the actual high performance building coming out of that construction, and then you have to spend additional resources to fix that building afterwards. Utilize your building automation systems. There's so much potential in the building automation systems that you could use. So set up the reports in a way that helps you track those savings, set up the alarms, set up the graphics, set up the trend data, and set up the reports in the building automation systems alone will let you sort of know the health of the building. In most cases, even up to 100% of the issues could be diagnosed using the building automation data, utility data, and intermeter data. Again, operator training and involvement is a key to sustain the savings. So if you're doing any projects around, whether that's a new construction, whether that's the decommissioning project, or whether that's operational excellence, I highly recommend it to involve your operations teams to get their feedback, help them understand what you're trying to accomplish, and help them involved in the whole process, so they see that sort of take the accountability and then sort of deliver and work with you to sustain those savings. And again, you can quantify these things, but in reality, some of these issues in the buildings um, would produce a sort of a big savings when they're fixed, because they have an after effect where which is not enabling other equipments to sort of perform it at the highest level. So um, having those small improvements not only help build the confidence within your team, but also lets you do the early wins and then help you set the stage for the bigger projects later down the road, which includes your heat recovery and other sort of capital intensive projects, and as you deliver those key savings. Last but not least, as I said, the first step is operational improvements. How do you know your building is operating as good as it is? The simple thing is look at the EUI for your building, compare against the target or high performance building. If there's zero savings potential, that means you're at the top of the benchmarking chart. That means your building has achieved most of the operational savings, and then you can focus on a lot of other capital projects around heat recovery and other aspects. But if you have a still savings potential of anywhere from 30 to 60 or even 10, 20, 50%, that basically is telling you that there's operational measures that needs to be done, that not only lowers their overall consumption, but it also sets the stage for a capital project. So for example, if you're doing a solar PV, or if you're doing a heat pump system or a geothermal system on an existing building, now you're sizing that system for the right load. You're not sizing it for sort of say a building that is inefficient, because that inefficiency could amount to 20, 30% of an extra consumption. So you're oversizing your system for the 30% extra consumption. Not only is that you're going to spend that extra capital on the 30% inefficiencies, but also that the immediate savings is not going to come into effect. Another thing I just want to mention is that sometimes there's a lot of facilities struggles with developing a business case for these measures. The simplest business case is to think it from that perspective. So if you have 30% savings potential in your building, that means that the paybacks are generally maybe less than sort of 3 to 4 years payback on those projects on operational savings. You could either invest that capital in the facility, or you end up paying the same amount of operating costs to utility companies. Not against paying to utility companies, but we would rather sort of recommend having sort of that consumption lowered down, which not only sort of helps you reduce your emissions, improve sort of your energy efficiency of the building, reduce your operating cost, but also sort of set the stage for the capital improvement. So the business case is to look into how much utility cost you're going to be paying over the next 5-10 years if you don't do those improvements, and consider those as a part of your decision-making process, not just only on the operating cost to do that, but also looking at the escalation rates of the utility cost over the next 5-10 years, and looking at that as another ways to sort of build those projects, and saving those additional costs will help sort of build that business case stronger and make it easier. That is all we had for today. I'm happy to address any of the questions, comments. If you have any, feel free to jump in anytime.
I think there's just one comment about, I think that's way back from the reducing heating of the makeup water in swimming pools, Namadeep.
Yeah, that's a great comment, and also an observation. It's around measuring the wastewater based on swimming pool loads helps reduce the heating of the makeup water. So definitely, if the facility has a means to that, or even if you have a means to sort of measure that sort of helps address how much sort of makeup water is going, which again, as the makeup water is coming in, if there's no preheat on their system, then you're conditioning that makeup water in the pools, and that's obviously energy being used in the pools. So absolutely, that's again a key data-driven observation that will let you know whether your pools is using a lot of makeup water or not.
Any other questions or comments? Okay, maybe we'll flick to the next slide. Amandeep. Oh, there's a question. Yes, someone just asked if the recording will be shared. Yes, the recording will be shared with everybody. I did post in the chat, a recording will be shared. We'll send it immediately to you. And we do post it on the Mayor's Megawatt Challenge website at some point as well. So that recording will be shared, and feel free to share it with others. I want to thank Amandeep for this in-depth exploration of how you can really address the opportunities in your buildings to save energy and get ready for net zero opportunities. If you wanted to get in touch with us, this is our contact information. And I want to thank all of you for attending today and listening to our webinar. Much appreciated. Have a good rest of your day. Thank you.